Well, hello AP Physics students. Welcome to another problem with Mr. Gersten. Today we're going to be checking out from chapter number 11, problem number 71. Alright, so here we go. Let's get to it. So there's a picture with this problem, and it looks like we have a sports car that's going to run into a giant spring. So let's check this out here. The problem states that our car here, which has a mass of 950 kilograms, is going to hit a giant spring. All right. So we are told the mass of the car is 950 kilograms. We're told that initially the car is traveling with a velocity of 22 meters per second. When the car hits the spring, it looks like it is compressed a distance of 5.0 meters. And the car compresses the spring. The spring then pushes the car back, and the car starts heading back the other way. And the question they have for us is two parts. A, what is the spring constant of this very large spring? And part B, how long is the car in contact with the spring? All right. Well, why don't we spring into action here? Holy cow, what is going on here? Well, spring stiffness constant. God, what do we know? We know something, we could use something like F equals kx, right? But we don't know what forces are involved. We don't know what accelerations are involved. We do know x, but we don't know F and k. So that's just not going to work for us. Well, sometimes when we don't know force exactly, we can use energy, the idea of energy. For instance, when the car is traveling towards the spring, we would know that the car would have kinetic energy. Well, what would happen to that kinetic energy when it hits the spring? Well, springs are an example of a conservative force. That is, the energy gets stored. And we could figure out how much energy is stored there with 1/2 kx squared. 1/2 kx squared is the work done in compressing a spring a distance x. All right, you can actually derive this formula from doing force times distance. All right, the force is 1/2 because it would be the average force as the force goes from 0 to kx. Anyway, this is the track I think we could take here. We could set 1/2 mv squared, the kinetic energy at the beginning of the problem, equal to 1/2 kx squared, the potential energy when the spring is compressed. And this would be a good way to solve for k. So our 1/2 would cancel out here, and if we do a little bit of rearranging, we would see that k would equal mv squared divided by x squared. So if we plug that in, we would get our mass, 950 kilograms, times our speed, 22 meters per second squared, divided by the distance x that the spring is compressed, 5.0 squared, and we would get a number that looks like 18,392. And of course you're thinking, oh, but Mr. Gersten, we only have two significant figures in this problem, and you would be absolutely correct in thinking that. So K, the spring stiffness constant, must be rounded to significant figures, 18,000 newtons per meter. Well, that is part A. Let's move on here to part B. Part B, what is the time that the car is in contact with the spring? Time. Well, gosh, how would we do this? Do we know velocity? Could we solve for acceleration? How could we solve for time? Well, we can't use traditional kinematics here. We don't know any of our variables that would let us solve for time using, say, a chapter 2 equation, a kinematics equation. So I think the idea here is to think about the position of the car versus the time it's in contact. So the car first makes contact with the spring, and the spring's in the equilibrium position. The car would then compress the spring and then get to some maximum decompression, compression I should say, and then come back. And then the car would be released here. So how much time is this? Well, this is 1/2 of a period, right? From simple harmonic motion, we know that the period should be 2 pi. The period of a mass on a spring is 2 pi square root of m over k. And we're claiming that our time would be 1/2 of this time. All right? So it would be in contact for 1/2 a period. So we could set this up and say t is equal to 1/2 of a period, 2 pi square root of m over k. Or the time of contact then would just be pi times square root m over k. Or pi times the square root of our mass, which is 950, divided by, we're going to go ahead, our stiffness constant, we'll go ahead and plug in as many digits as we know here. And if we plug that into our calculator, we get a time of about 0.71 seconds. All right, nice work, AP Physics students. So 1/2 of a period is the big idea there. Well, thank you for your attention. I have something better than a joke for you today as your reward for listening. I have, are you ready? Holiday shopping suggestions. So, Mr. Kirsten, where do you go holiday shopping? Well, for my four-legged friend that you got introduced to last video, I got, check this out, at Menards today, less than $5. Here we go. A 24-inch, oh, I don't want Raven to hear, a 24-inch rawhide chew, all right? Check these out. They're at Menards. So that's a great holiday shopping gift if you have any four-legged friends. Oh, hi, Raven. We're not talking about anything here. Yep. What's another great gift idea for the holiday? Dun, dun, dun. You can also get this at Menards. Check this out, you guys. This is so cool. Anyone in your family would love to get one of these for Christmas. This was $10 at Menards. It is an LED light bulb, right? It's a 60-watt bulb, only takes 12 watts. Can you imagine? How cool is that? Look, there's no mercury, no lead in this. And look, you know about a gift that keeps giving all year long? Think about a light bulb that a Christmas gift you could get for someone that would last 22.8 years and they could use 3 hours a day. Think of how much time and carbon dioxide you could save a loved one if you got a great Christmas gift like this. I actually got 2 of them. I'm going to give one to my sister and one to mom and dad. What a great idea for holiday giving. All right, nice work, AP Physics students. We will see you in class tomorrow.